When estimating building electrical loads to properly size generator capacity without oversizing, several resources, methods, and considerations can be helpful. Published references offer valuable guidance. The ASHRAE Handbook HVAC Applications, specifically Chapter 33, provides guidelines and tables for estimating electrical loads in commercial buildings considering building type, occupancy, and climate. The Energy Efficient Building Design, a guide published by the California Energy Commission, includes load calculation methods and tables tailored for commercial buildings. Power System Analysis and Design, 6th edition by J. Duncan Glover, covers methods for estimating electrical loads in power systems with specific relevance to commercial buildings. IEEE Standard 3007.2020 provides recommended practices for estimating electric power demand for commercial and industrial facilities. The IEEE Green Book, also known as the Emerald Book, contains guidelines for designing energy-efficient electrical systems, incorporating load calculation methods. Design guidelines offer alternative approaches to NEC demand calculations. The percentage method assumes that a certain percentage of the total connected load will be in demand simultaneously. This percentage varies based on the building type and occupancy. For example, a school may have a demand factor of 30 to 40%. The diversity factor method considers the probability that not all loads will operate at their peak simultaneously. Diversity factors are available for different equipment types and building zones. If available, historical data analysis from previous similar buildings can be used to estimate the actual peak demand. Load profiling, achieved through detailed monitoring of electrical consumption, can provide insights into the building's actual load patterns, which can then be used to optimize the sizing of the generating capacity. Several key points should be considered. Firstly, the demand load calculations in the National Electrical Code are intended to ensure safety and reliability, but they are not meant to be an accurate representation of actual demand. Secondly, factors such as building efficiency, occupancy patterns, and equipment scheduling can significantly impact the actual demand. Thirdly, consulting with the client is important to determine their specific requirements and provide them with reassurance that the design is based on recognized methods and industry best practices. To elaborate further on these methods and resources, consider the application of the percentage method. This approach acknowledges that not all connected electrical loads within a building will operate at their maximum rated capacity simultaneously. To apply this method, you need to determine the reasonable percentage of the total connected load that is likely to be in use at any given time. This percentage is known as the demand factor. Demand factors vary depending on the type of building, its occupancy, and the nature of the electrical loads present. For instance, a hospital may have a higher demand factor than an office building due to the continuous operation of critical medical equipment. Schools, as previously mentioned, often exhibit demand factors in the range of 30 to 40%. To implement the percentage method, you would first calculate the total connected load of the building by summing the ratings of all electrical equipment, including lighting, HVAC systems, appliances, and machinery. Then, you would multiply the total connected load by the appropriate demand factor to arrive at an estimate of the maximum demand load. For example, if a school has a total connected load of 1000 kilowatts and a demand factor of 35%, the estimated maximum demand load would be 350 kilowatts. The diversity factor method builds upon the concept of the percentage method by taking into account the diversity of electrical loads within a building. This method recognizes that different types of equipment have different usage patterns and that their peak demands may not coincide. Diversity factors are used to account for these variations in usage patterns. For example, a lighting system may have a different diversity factor than an HVAC system, reflecting the fact that lighting loads tend to be more consistent throughout the day while HVAC loads fluctuate depending on weather conditions and occupancy levels. To apply the diversity factor method, you would first divide the building into different zones or load categories such as lighting, HVAC, appliances, and machinery. Then, you would assign a diversity factor to each zone or load category based on its expected usage pattern. Diversity factors are typically expressed as ratios, with values less than 1 indicating that the peak demand of the zone or load category is less than its total connected load. To calculate the estimated maximum demand load for the entire building, you would sum the product of the connected load and diversity factor for each zone or load category. For example, if a building has a lighting load of 200 kilowatts with a diversity factor of 0.8, an HVAC load of 300 kilowatts with a diversity factor of 0.6, and an appliance load of 100 kilowatts with a diversity factor of 0.4, the estimated maximum demand load would be 200 kilowatts times 0.8 plus 300 kilowatts times 0.6 plus 100 kilowatts times 0.4. which equals 160 kilowatts plus 180 kilowatts plus 40 kilowatts for a total of 380 kilowatts. Historical data analysis involves examining past electrical consumption patterns in similar buildings to predict future demand. This method is particularly useful when designing new buildings that are similar in size, function, and occupancy to existing buildings for which historical data is available. To perform historical data analysis, you would first gather electrical consumption data from existing buildings that are representative of the building you are designing. This data may include monthly or annual energy consumption figures, as well as more detailed information on peak demand, load profiles, and time of use patterns. The data can be obtained from utility companies, building management systems, or energy monitoring systems. Once you have collected the historical data, you would analyze it to identify trends and patterns in electrical consumption. This may involve calculating average energy consumption per square foot, peak demand per occupant, or load factors. You would also look for any seasonal or daily variations in electrical consumption. Based on your analysis of the historical data, you can develop an estimate of the expected electrical demand for the new building. This estimate should take into account any differences between the new building and the existing buildings from which the data was collected, such as differences in building design, equipment efficiency, or occupancy patterns. Load profiling is a more sophisticated method of estimating electrical demand that involves monitoring the building's actual electrical consumption over time. This method provides detailed insights into the building's load patterns, which can be used to optimize the sizing of the generating capacity and improve energy efficiency. To perform load profiling, you would install energy monitoring equipment at various points within the building, such as at the main service entrance, at individual distribution panels, or at specific pieces of equipment. The monitoring equipment would collect data on voltage, amperage, power factor, and energy consumption over a specified period, typically several weeks or months. The collected data would then be analyzed to create a load profile, which is a graphical representation of the building's electrical demand over time. The load profile can reveal valuable information about the building's electrical consumption patterns, such as peak demand, base load, daily and weekly variations, and the contribution of different types of equipment to the overall load. Based on the load profile, you can develop a more accurate estimate of the building's maximum demand load and identify opportunities to reduce energy consumption. For example, you may discover that the building's peak demand occurs during a specific time of day due to the operation of certain equipment, and you can then implement strategies to shift or reduce the load during that time. In addition to these methods and resources, it is important to consider several other factors when estimating building electrical loads. These factors include the building's climate, occupancy patterns, and equipment scheduling. Climate can have a significant impact on the building's electrical demand, particularly for HVAC systems. Buildings in hot climates tend to have higher cooling loads, while buildings in cold climates tend to have higher heating loads. Occupancy patterns also play a role in determining electrical demand. Buildings with high occupancy rates, such as schools or office buildings, tend to have higher lighting and equipment loads than buildings with low occupancy rates, such as warehouses or storage facilities. Equipment scheduling refers to the timing and duration of equipment operation. By carefully scheduling the operation of equipment, you can reduce peak demand and improve energy efficiency. For example, you can schedule the operation of non-critical equipment, such as water heaters or air compressors, during off-peak hours when electricity rates are lower. When selecting a method for estimating building electrical loads, it is important to consider the available data, the complexity of the building, and the desired level of accuracy. The percentage method and diversity factor method are relatively simple to apply and require minimal data, but they may not be as accurate as historical data analysis or load profiling. Historical data analysis requires access to historical data from similar buildings, which may not always be available. Load profiling provides the most detailed and accurate estimate of electrical demand, but it requires the installation of energy monitoring equipment and the analysis of large amounts of data. Ultimately, the best method for estimating building electrical loads will depend on the specific circumstances of the project. It is often helpful to use a combination of methods to validate the results and ensure that the estimate is as accurate as possible. Additionally, consulting with experienced electrical engineers and energy consultants can provide valuable insights and guidance. Remember that the goal is to accurately estimate building electrical loads in order to properly size generator capacity, avoid oversizing, and ensure the safe and reliable operation of the electrical system.